Hey, this is Horner. We're going to look at 17.1 electric potential energy. So electric potential energy is just like any other potential energy. It's energy that is stored, and here it's stored in an electric field. So we've been talking about electric forces, and then we talked about electric fields. Now we're going to talk about the electric potential energy. For gravity, we know that anything that's really high up in the air has a high gravitational potential energy, and as it falls, that energy is converted into kinetic energy, so the potential energy gets lower and lower and lower. High electric potential energy, you'll notice, is signified by a positive charge, and that positive region has a higher electric potential energy. And it's because if I take a positive charge and put it here, it would be pushed in this direction toward the region of lower electric potential energy. For this surface is a negative charge. So we have negative charges on one side and we have positive charges on the other. So here a lot of energy because they're trying to push each other apart, and then a little bit of energy, well, energy is lost basically as it moves from the positive to the negative side. So we're going to use a lot of gravitational to electric potential energy analogies to help you kind of understand those. So for both of these, the change in that potential energy is work. And so the sign here is opposite because there's work done by the field. And the amount of work or the amount of energy is taken from that stored potential energy, so it dips into that tank. So essentially what you could do is you could think of, if I had a circle, let's try a better circle here, that didn't work out really well. If I have a circle, whoa, there we go again. If I have a circle and I have energy, okay, that's changed. So let's say that this graph represents electrical energy, so we're going to just put UE. And we start with 4 bars of electrical energy here, so we'll do 4 bars, but then I only have 1 bar of electrical energy on this side. Something had to happen to that energy. Well, it didn't go in, it actually had to come out. So what I like to do is just do this little system chart. So my system, I actually had energy that was pulled out of that system. So that's why you see this negative work. And we would actually, on this arrow, then put work going out. And whenever work goes out, that means that our work done by that field is negative. So that's why you'll see that negative sign on the change and the potential energy due to that electric field. For the next part, this is really important. Here the connection is, there's a lot of different similarities between gravitational and electric potential energy. So remember, gravitational potential is UG, and we're going to do electric potential energy as UE. And that way we can separate the two. In both cases, this depends only on the position. So where they're at does not depend on the path. So we don't worry about the path. We can go any way we want to. So if I have 2 plates, let's say that one plate is positive and I have one plate that's negative, and I put a positive charge right here, what will happen is the positive charge will move from one side to the other. And when it does that, it can go straight across, or it could do this loop-de-loop and then go over here. But the change in energy, the change in the electrical energy is the same. So it's not the path that matters, it's just the starting and the ending point. So sometimes I tell students, think about taking a picture here and a picture when it's at the end, and you'll realize that the path really doesn't matter. So only the changes in potential energy are significant. So we can assign that potential energy to be 0 at any convenient point that we want to, but it needs to only be at one point. And if we have a couple of different particles, we usually choose U equals 0 when they're really far apart. So if I want to know the potential energy between these two particles and we say that they're extremely far apart, that potential energy would be equal to 0, so the electrical potential. So those are some connections that you can make between gravitational potential energy and electrical potential energy. So both of these are exerted by a point particle, and we know that the force is inversely related to the square of the distance. So we see that for force in both this equation and in the equation that we have for charge. So this is Q1, Q2 all over R squared. So we see the same thing in both. This is the force due to gravity and the force due to electrical force. Um, the gravitational force and gravitational potential for a point particle pair are proportional to the masses of the particles. And so for what we're doing, we say it's proportional to the charges themselves. Notice that the potential energy here only has one R in it, and the force has that R squared. And that'll be important when we look at the equations for electrical force and electrical potential energy. So here are the corresponding equations. This is the electric force, and it's KQ1, Q2 all over R squared. So the only things that have changed here, remember, is this for the force due to gravity is G, and then these are M1 and M2 for Q. This, same thing, and here we do have KQ1, Q2 over R and not over R squared, similar to what we have for the potential energy due to gravity. And you might notice that there's no negative here, and we do have a negative on the one for gravity. We'll talk about it a little bit later. These are some graphs that show us the relationship between that potential energy due to gravity. So here's the gravitational attraction, and you'll notice that all this energy, UG, is negative. You'll also notice that the potential energy here, if Q1 times Q2 is less than 0, then the potential energy here is negative. So the electric potential. But now we also have Q1 times Q2 is greater than 0. That means that I have two oppositely charged particles and two similarly charged particles. And if that's true, then I'm going to get a repulsion. And here I'm going to say that UE is positive. So for attraction, you'll notice that you get negative potential, and for repulsion, we get positive potential energy. And so those are really important. For the very first example we have here, this is a classic example. You have a thundercloud, and so here's the very high thundercloud. These could be 30, 40, 50,000 feet high in the air. And so this is 8 kilometers, and you'll notice that at the top, the charge on the thunderstorm cloud is 50 coulombs, and on the bottom it's negative 20. And so we have an electric field, and remember, electric field always goes from positive to negative, so you've got this huge electric field that's generated on the inside. Because of that, you're also going to have a lot of electrical energy, and eventually you're going to have some discharging, kind of like you'll see with the Van de Graaff generator, and that's where you get the lightning. So it can be all kinds of lightning. So this is bottom of the cloud to the ground. Sometimes you'll get top of the cloud to the bottom of the cloud, and a lot of different types. So we'll look at those later. They want to know in this, what is the electric potential energy of the pair of point charges, assuming that U equals 0 and the two are infinitely far apart. And then they want us to explain the sign of the potential energy in light of the fact that the positive work must be done by external forces in the thundercloud to separate the charges. So we've got to have something happen in order for those charges that we see in the previous slide to actually separate those charges out, so we have that that separation of charge and then all the energy generated. So the electric potential energy for a pair of point charges, remember the equation where we said UE is equal to 0 at an infinite. So infinite here just means as far away as we can get them. The work done by the external force to separate the charges is equal to that change in the electric potential energy as the charges are moved apart. So we will look at each one here. Let's do the first one. We know that UE is equal to KQ1, Q2 all over R. So we've put in our 9 times 10 to the 9th for our constant. Here's the 50 coulomb positive charge at the top of the cloud, the negative 20 at the bottom, and then remember it was 8 kilometers, and we've got to keep everything in kilograms, meters, and seconds. So this 8 kilometers needs to go away, and we need to use 8,000 meters. So at this point we have negative 1 times 10 to the 9th joules. Notice that your energy here does become negative because I have two charges that will attract each other. If they're attractive, then the change in energy should be negative. That is part of letter A. Now let's go ahead and go to the next part, which is letter B. Here it says that U equals 0 at an infinite separation. So negative potential energy means that if the 2-point charges are really far apart, their electric potential will decrease as they're brought together. In the absence of other forces, they basically would just fall towards each other. But in the thundercloud, unlike charges that start close together and then move further apart, there's something that we've got to have to do positive work to increase the potential energy and have those charges come apart. So initially, when the charges are close together, that potential energy is really less than -1 times 10 to the ninth. So that change in potential energy as the charges moves, as those charges are moved apart, is positive. So in that great big thundercloud that you've got like this, those charges, when they're infinitely apart, they were at some point probably together. And so you might have had the positive and the negative charge down here because they are attracted to each other. But you got to remember there's a large amount of wind and an updraft that happens here just by convection. So we've got cooler air down at the bottom, warmer air at the top, and the air rushes up. And so some of those charges will have to have some work done to have those separate. Alrighty, so that's 17.1. Let's go ahead and look at this situation if we have several point charges. So if we have more than 2-point charges, so if we have more than 2, we need to add the potential energy of each pair of the charges. So for 3 charges, you're going to use the equation, and they really start out with K, Q1, Q2 all over the position or the change between R1 and R2. Plus, and then there's K here, Q1, Q3, all over 1, 3, plus, and then the last one, K, Q2, Q3, all over R2, 3. But because the K is a constant and it doesn't change, we can put it out front. We don't have any of the tops. You'll notice that we only have 1 in these two, we only have 2 in these two, and we only have 3 in these two, so we can't separate and put the charge out front, of course. So here the potential energy is the negative of the work done by the electric field as the 3 charges are put into their positions, and that starts from an infinite separation. So remember we said U is equal to 0 when our R is at an infinite separation. This is a good example of kind of what to do when you have those 3 charges. So they want us to find the electric potential energy for, and they call this an array because they're at certain positions. They gave us each one of the charges and they told us kind of some distances here. Well, they actually told us the positions where they're at, so we can find the distances as we go through. We're going to use these 3 charges. We're going to have to find the sum. The charges are given. We just have to find the distances. So once we do that, we can then plug it into our equation. So the very first thing we have to do is figure out what the distances are. This one's pretty easy. It's just 3. We know that this distance here is 1, 2, 3, 4. So this is 4 meters, this is 3 meters, and now I have a triangle which is a 3, 4, 5 right triangle. If you don't know about 3, 4, 5 right triangles, then you could use the Pythagorean theorem, where we just said that we square this side, square this side, square this side, but we don't know what it is, so we're going to do the square root. That'd be the square root of 25, and that gives us the 5. Here's our equation. The potential energy is the sum of all the potentials between the particles. And so the first one I want to look at is between 1 and 2. So here's number 1 and number 2. Our distance is 5 meters, that's why it's here. And then we have Q1, which is positive 4, and we have Q2, which is positive 2. Now remember, these two will repel each other, but we just put our signs in, everything will work out in the end. The next thing we need to do is look at Q1 and Q3. So Q1 is plus 4, Q3 is negative 3, the distance is 3. So this one's going to be negative. And then this one is negative 3 times 2 divided by the distance, which is 4. So this one's also negative. We go ahead and do all of our math, and once we've done that, we end up with, and remember, this really is point is really 4 times 10 to the negative 12th, so they actually factored out that 10 to the negative 12th. If you don't want to do that, you can leave them in, but it's nice to take them out and put them on the outside of the parentheses, because then that way you're just dealing with whole numbers instead of these really, really small whole numbers. Once you're done, you do all your math, you'll end up with potential energy of negative 0.035 joules. So when you're done, you just kind of want to make sure that it makes sense, and that one made sense. So we will then go on to 17.2 and the next PowerPoint slide.